Good evening, class. I am Omar Gonzalez. I'm a research paper is the Empowering Convolutional Networks for Malware Classification and Analysis from the Technical University of Munich, Germany. Here's the introduction. This paper explains a neural network's performance as an approach to attempt a classification model of malicious executables. The neural network used was a hybrid architecture that combines feed-forward layers and convolutional layers. It embodies a hierarchical feature extraction approach that combines convolution of n-grams instructions with plain vectorization of features from the portable executable file. And the background is the n-gram. In this case, is a contiguous sequence of n instructions in malware analysis classification. It is important to know the portable executable format of binaries. The P file header shows dynamic link library and imported functions. The timestamp from the compilation, their sizes, and the disk and memory. We can also analyze the source code under sections such as text, data, and other sections. And the code can be disassembled into assembly representation to extract possible features. A convolutional network can be applied to extract high-level features for short texting using convolutional filters, since logs containing instruction from malicious executables consist of sequence of words from a predefined dictionary. There's an obvious analogy with text documents when selecting modeling methods. The dataset was a set of malware samples from virus share and private collection. Object dump was used to retrieve operation code and PE info to extract information from the executable header. Features of the PE files were extracted by pre-processing the fields of the header and the opcode from the code section. The metadata is at 27 features, which consists of compile time, address offset to image resources, sizes, virtual addresses, and more. Import features consist of imported functions and their DLL files. 488 unique functions. The assembly opcode feature is assembly instruction of PE files. The opcodes were converted into a matrix representation. Each row is a vector representation of one opcode. Signature clustering, Boolean label, vectors were created for every malware sample that represent presence or absence of signature given by different antivirus engines. The sample signature vectors are clustered using dbScan. Here is at the table that shows the 13 clusters with the highest number of members as families for classification. Here is the hybrid neural network architecture, which is a feed-forward layer with its 27 features from the PE metadata and 488 Boolean features from the PE import list, and convolutional layers with its opcode features. The hidden layers in the feed-forward have 500 units. The convolutional network learns the semantics of the instruction usage patterns to identify benign and malicious. The second hidden layer from the feed-forward neural network and the pooling layer from the convolutional neural network are aggregated into one layer. Then a fully connected layer of 13 softmax units used to generate the final classification output. Here are details of the convolutional layer. The width of the filters is 118, which is equal to the dimensionality of the opcode, and which is the height of the filter represents the number of adjacent opcodes varies among different variants of the model. The filter heights 2, 3, 4, and 5 were experimented with 10 features maps each. The height 3 gave the best result. The data set was 2000 for evaluation. The data set was 22,757 executable, 22,794 malicious, and 63 benign from the CDNets download list. The graphical processing unit was CUDA. The neural network models were trained with Lagrange and TensorFlow libraries, and to extract features, the Python programming language was used inside Py and NumPy. And the classification, 1v9 class and multiple malicious classes. The performance metrics used was precision recall and F1 score. It was a threefold validation, cross-validation experiment where two partitions for training and one remaining for testing to measure the hybrid neural network performance gain. A support vector machine classifier was also trained. Table 2 is a classification performance, and we can see that the hybrid neural network, it shows a better precision recall and F1 score than the other, the feed-forward, convolutional, and the support vector machine. Here, Table 3 depicts the average of the classification performance for each of the classes of the hybrid neural network. Also, it reveals the samples belonging to 1, 4, 5, and 7, which are highlighted in green, as well as the benign samples are approximately correctly classified. In contrast, samples belonging to 0, 2, 10, and 11, highlighted in pink, are misclassified. Table 4 shows the confusion matrix. We can see that the classes 0, 2, and 11 highlighted are confused with class 3 because they share common malware signatures. Figure 3 represents the average activation value of the input feature for 10 malware samples of class 1. The most active neurons are assembly opcode features, which indicate they are the most significant contribution to malware classification. Here, the high dimensional activation of the neurons are at the hidden layer, where projected a lower dimensional space for visualization analysis. The features points for class 1, 3, 4, 5, 8, 12, and 13 within green color are well separated. However, there is a confusion among classes 6, 7, 9, and 10 within the red color. This approach demonstrates the robustness against instruction reordering as well. Given 150 samples, their corresponding sequence of opcode were randomly shuffled. The hybrid neural network approach shows F1 score values of above that 90 until 50% rate of shuffling. Additionally, this test was performed on the support vector machine, but its performance decreased to an F1 score of value that 82 while increasing the rate of instruction shuffling. Here the salient maps. It shows that the reason for classification results, we can see that the chosen sample should be given a label 7 according to most of the P features, yet there is a significant peak at the feature with a number 34 that indicates that the sample has also characteristic of class 10. This feature is the size of a certain P resource field in the file header. Here are the limitation and feature work. The neural network was used a data set of the result of a static malware analysis. There are ways to obfuscate code that the network cannot handle. It was not considered the appearance of malware from unknown family. And in dynamic malware analysis, malware behavior during execution can be extracted. To conclude, this neural network consists of convolutional and feed-forward layers that uses metadata of PE files, imported functions, and series of opcode to separate malicious executable from benign programs and classify malware into 3 predefined classes. The evaluation results demonstrate that a hybrid architecture approach outperforms baseline methods such as simple feed-forward neural network and support vector machine. The precision and recall were 93 and the F1 score was 92. Any questions?